Hello and welcome back to another episode of Math with Son. Today we're going to be talking about velocity versus time graphs, where yesterday we talked about position versus time graphs. So one thing that's very important to recognize is that velocity versus time is going to do all of the same things that position did, but towards acceleration. Because when you're moving down the line from position to velocity, to acceleration, the attributes stay with it. So for instance, when we had the position graph, the slope was the change in position over time, and that was equal to velocity. Here, the slope is equal to the change in velocity over time, which means that it is going to equal the acceleration, because acceleration is how quickly your speed, or your velocity, is changing relative to time. So when the positive slope for velocity time graphs occur, you have a positive acceleration. When you have a negative slope, you have a negative acceleration. And if you have no slope, you have no acceleration. Okay? Now that is very important to distinguish between when you could interpret acceleration versus the position graphs, because on the position graphs, it was the curving of the graph that determined if you had acceleration or not. Okay? So if it was curved upward on a position graph, that would indicate you had positive acceleration, versus if it was a frowny face, curved concave down, that would indicate negative acceleration. Here, you have the slope of your graph, and that determines if you have acceleration at all, period. If you have a positive slope, you have positive; negative slope, negative acceleration. And if it's flatlined, if you have no change in velocity, you have no acceleration. Okay, so the only time you're going to have no acceleration with velocity versus time graphs, if it's a straight line. Okay, speed is neither determined with direction. It is a scalar, so the absolute value of your speed would equal your velocity. All right. So one thing when you're asked about speed, you need to be very careful. Speed doesn't care if it's negative or not. So for instance, down here we have a negative velocity, but that doesn't mean that we don't have some speed occurring. So here we have potentially the highest speed in your entire graph system, because it's the lowest, and it's lower than any high point we had up here. So this dot right here would indicate the highest speed, but it would also indicate the lowest velocity. All right. Anyways, while we're dealing with this, we got positive acceleration here because the positive slope, no acceleration because the slope is constant. Negative acceleration during this entire strip, we have negative acceleration, but because here we have a positive velocity and a negative velocity, that indicated that we were slowing down, not speeding up. We were slowing down, and then we had negative velocity, meaning we changed direction, because right here we were in positive, we were going to the right, and now we've changed to negative, we're going to the left. And then here, this would not indicate a change in direction. This would indicate that we are finally stopped, like slowing down in the negative direction, and we started going towards the positive direction, but we haven't gotten there yet. So that would indicate that we are still negative velocity. It gets a little confusing. Don't worry about it too much. All right. If the graph is approaching the x-axis, that would indicate the velocity is getting closer to 0, versus if it is moving away from the x-axis, that would indicate that the velocity, or the speed specifically, is speeding up. Okay, because it relates to positive and or negative. The further away you get from the x-axis, the quicker and quicker your object is becoming, whether it is in the positive right direction or negative left direction. All right. Displacement. Velocity is a positive, and displacement is indicated by how far you have moved. Well, delta x is equal to your velocity times time, it makes sense because you've probably heard this formula before. Distance is equal to rate times time. Well, if distance is equal to rate times time, you may notice that this is your rate and this is your time. So your displacement is your area under the curve. So your displacement, or your delta x, is your area under the curve. And if your area under the curve is your displacement, you can find that by either using, in this case, the area of a rectangle, length times width, which is volume times time. But in other cases, if your area is a triangle, you might have to think a little bit more carefully about how to find the area of a triangle, which is 1/2 base times height. All right, I got one example for you to find some stuff. Find the displacement of the object after 55 seconds. So 55 seconds is, the whole time. That's going to be annoying. We will have to find the area of every single bit of this and pay attention to the fact that if it is below the graph, that is going to involve a negative area because we have gone backwards, okay? So first we're going to do this area of this little triangle right here, which is 1/2 base times height. The base is 10, the height is 60. So we got 1/2 10 times 60 plus the area of this little rectangle, which is 5 by 60. So far we've done the triangle and we've done this little rectangle right here. Then we have this triangle, which is 1/2 base times height, which is a base of 15 and a height of 60. So plus 1/2 base, which is 15, times the height of 60. And then we're going to have to subtract this triangle. And this triangle, you can either do the left half and the right half, or you can recognize the height is 40 and the base is from 30 to 55, the 30 to 15, it's 25. The base is 25. This part right here to here is 25. So minus 1/2, 25 base times height of 40. I am going to utilize a handy dandy calculator. So we got 0.5 times 10 times 60 plus 5 times 60 plus 0.5 times 15 times 60. This positive portion was equal to, this positive portion was equal to 1050. And then the negative portion would be minus 0.5 times 25 times 40. I already subtracted it. If we subtract it, we get from the 1050, taking away, it seems like 500, this chunk looks like 500, you get a total displacement of 550 what? Well, displacement is in terms of distance, and that would mean 550 meters. All right. Find the distance the object traveled in 55 seconds. Well, displacement is different than distance. We found out all the math for it already. We got 1050 on this positive part, meters, and then instead of subtracting this bottom triangle, we have to add that amount, which would be adding 500 meters, which is the 1/2 times 25 times 40, and that equals 500. And when you combine those, you get 1,550 meters total in distance. Find the acceleration and speed at 30 seconds. So the acceleration and speed at 30 seconds. Well, the speed at 30 seconds is at 0. So the velocity is 0 meters per second. But the acceleration, remember the acceleration is the slope. The slope at that time. Well, the slope at that time is on this constant negative facing line, which went down by 1, 2, 3. Well, down by 60 and over by 1, 2, 3, 15. Negative 60 over 15 seconds would equal negative 4 meters per second squared, which I'm going to take a second to do the units for that. We have negative 60 in the velocity direction, so negative 60 meters per second divided by 15 seconds. Well, negative 60 divided by 15 seconds, if you think about that in terms of fractions, negative 60 meters per second divided by 15 seconds, you would still get the negative 4, but if you're dividing by seconds, that means that the meters per second would end up dividing by another seconds, which ends up being meters per second squared. Okay, so that kind of tells you how acceleration is meters per second squared. Name a time when the velocity is increasing, but the speed is decreasing. Okay, so for the velocity needs to be going up, but the speed needs to be going down. Well, I would indicate that would be this chunk right here. Because the speed in this chunk right here is decreasing because we went from 40, essentially meters per second for speed, and we're going towards 0 meters per second speed. But the velocity was negative and now it's approaching positive. So that would be when your velocity can increase and your speed could decrease, is whenever you have the velocity being negative and it going towards 0. So from 40 to 55 seconds, 40 to 55 seconds, not inclusive. So that's why there's parentheses there. Name a time when velocity is decreasing, but the object is getting faster. So that would be the opposite chunk right here. Here, where we are decreasing in velocity because we're getting further into negatives, but we're increasing in speed because the speed is scalar. So that would be this chunk right here from 30 to 40 seconds, not inclusive again. All right. Actually, hang on. No, only that chunk. Because over here, once we approach positive, the speed would have decreased briefly and then started increasing again. All right, that's going to do it for this one. Until next time, stay positive, everybody, and I will see y'all later. Tomorrow, we are doing acceleration versus time graphs, so I will see you then. Bye.